My name is Dharshan. I'm the founder of ScaleGrid.io. At ScaleGrid, we build database as a service solutions, and we specialize on NoSQL databases, particularly MongoDB, Redis, Elastic. So over the past 4 years, we have run thousands of Mongo instances on AWS and Azure, and we have learned several things along the way. So in this presentation, we're going to share some of our learnings. It's kind of like a high-level architecture presentation. I'll go over 10, 12 different aspects, some functional, some non-functional. We won't go into the depth in each of these topics, but it's enough depth for you to be able to ask the right questions as you start going through this process. And we have a small audience, so it's after lunch as well, so I want to make it more interactive. So if you guys have questions, or if you have any observations, feel free to raise your hand and we can discuss about it. So before we get started, right? So how many of you folks are actually using MongoDB? It's not bad. In production? Okay. And which clouds? AWS? Azure? Other? Okay. Sure. Sounds good. So let's start with some, MongoDB 101. So in terms of high-level configuration, MongoDB supports 3 basic configurations in different types. So the first option, of course, is standalone instances. These are just single servers, and typically you should just be using them for dev and test. But you'd be surprised how many people actually run production systems on a single instance. So we highly discourage that, but people do it anyways. So the next configuration we're going to talk about is the replica set configuration. Think of the replica set as your master-slave equivalent in MongoDB. And the operations are a lot simpler than MySQL. So essentially you have a master, and you can have multiple slaves. You can only write to the master, and all the writes are synced to the secondaries. And you can have up to 50 secondaries. And the secondaries can either directly sync from the master, or they can sync from other secondaries to have a chained configuration. And even though you can have 50 nodes, you can have a maximum of 7 voting members. It's only 7 that can decide which one is going to be the next master. And in case there is a failover, if this node goes down, the other nodes will get together, and if there is a quorum, they'll vote a new master, and things will go on. There'll be a slight downtime while the election happens, but that's the failover process. And the failover typically, it used to take about 30 seconds in the older versions of Mongo. Now they've reduced it to less than 5 seconds on average. Now the interesting thing about the replica set configuration model is that it's not a write scaling model. All your writes are still going to the primary, so you can't scale your writes beyond that server. But what you can do is, with this model, you can scale your reads. Essentially, what you do is, if you want more read throughput, you can keep adding secondaries. So it's a write once, read many time model. And of course, in that model, you need to be careful. You need to be watching the replica lag on each one of these secondaries. Because, again, it depends on your application model, but you might not want the secondaries to fall back a lot behind the primaries. So essentially, this is a read scaling model. And of course, it's a high availability model. Mongo also has this concept of arbiters, where instead of a full secondary node, you can have a small instance. They call it the arbiter. And essentially, it doesn't hold any data. All it has is a vote. So essentially, it helps to vote in the quorum. So when we talk about 2+1 models, that's what we mean. It's 2 full-size nodes plus an arbiter. And the advantage is, you need 3 nodes to basically do a failover, and the arbiter gives you that. And at lower cost, of course, because you're not paying for another full-size instance. And in some ways, HA is built into Mongo. So that's, when you move from MySQL to Mongo, that's something you like, because you don't have to go set up a parallel system and debug it and walk through it. It kind of all works by itself. The last cluster is basically a sharded cluster. This is a scale-out cluster. And this is essentially the money cluster, This is the real reason you end up using Mongo, so that you can easily deploy it and scale it out. And you can essentially do both read scaling and write scaling. So Mongo has this concept called shard, which is similar to any other sort of scale unit. So these are the scale units. Now each one of these scale units can be a replica set. You can have a 2+1, 3, or however you want. So you define your scale units. And in front, you have this concept of shard routers. Shard routers are similar to your proxy servers in MySQL. Essentially, the application essentially connects to the shard routers. And the shard routers handle all the routing to go from this server to the actual shard. Shard routers are stateless. There's no data stored on them. All they are is a forwarding connection. And there is another set of servers called the config servers. Typically, there are 3 of them. And essentially, they just store simple metadata information about the cluster. So essentially, in case of sharding, they basically, store, which range goes into which shard. So basically, when your write comes into the server, the shard router will look up from the config server. In most cases, it's cached, which actual router it has to hit, and then it goes directly to the shard router. So this way, let's say you want to do your scale, or you want to scale your reads, or you scale your writes, you essentially keep adding more shard routers and more shards. And theoretically, it just scales linear. And it all just works out of the box. So you don't need to go build a failover solution, or you don't need to understand quorum or stoneth and all the different things. So the operations get a lot easier. Now let's talk a little bit about high availability. So I'm going to define high availability in very simplistic terms. Essentially, your cluster should still continue to work if you have like a server failure or if you have like a rack failure, right? So essentially, if you have a standalone instance, which is a single instance, you essentially have no high availability. If if that particular machine goes down, or if that particular rack goes down, essentially your server is toast. So if you want high availability, at minimum, you should be deploying a replica set. You can deploy a 2+1 or a 3-node replica set. And essentially, the availability impact is the same. You can take one failover. If you have a 3-node replica set, because the other 2 nodes still have quorum, they'll continue to work fine. If you have 2 failures, essentially what will happen is the one remaining node doesn't have quorum and it goes into read-only mode. So that's the advantage of having a replica set. Now, most of the references I'll have in this document when I refer to public clouds, I'll refer to AWS and Azure. But the same model applies to any other public cloud that you plan to use. Most of them just follow the same model anyways. So if you are deploying a highly available replica set in AWS, you definitely want to consider distributing them in different availability zones. AWS calls them AZ. Think of them as independent data centers. They are typically in the same city, but they're usually 15 to 20 miles apart. And there's no shared hardware and things like that. So what AWS does is it guarantees that not more than one AZ will be down at a time. It doesn't always work. Sometimes the whole region goes down. Like it happens in US East. But that's a rare event. And I'll talk more about it. It's a business decision that you need to make, whether you need to prepare for that, because it's a lot of work to be ready for that. For most people that we see, they're perfectly happy with just AZ level failover. And they essentially deploy a 3-node replica set, one replica in each AZ. And then at that point, you're guaranteed of having high availability. Now, there are some regions in AWS that only have 2 AZs. Like if you go to, I think, Singapore, and ironically, Northern California has only 2 AZs. You'd figure that, it'll be a hotbed, but apparently not. So it has only 2 AZs, and in a region with only 2 AZs, you can't really deploy a highly available replica set. Because whatever you do, one AZ will end up having 2 nodes, and if that AZ goes down, essentially your replica set doesn't have quorum and will go down. So that's something to keep in mind as you deploy replica sets in AWS. Now Azure has a similar models. It doesn't have any concept of AZs. Azure has an interesting concept called the availability set, and it's based on 2 underlying properties. They are called update domain and fault domain. Now, whenever you define an availability set in Azure, it basically gives you 5 update domains and 3 fault domains. Now, what the update domain is used for is essentially any sort of planned maintenance from Azure. Like, for example, Azure might need to upgrade their routers, or they might need to upgrade their hardware. So what they will do at that point is they'll walk the upgrade one update domain at a time. And essentially, each availability set has got 5 update domains. So what you want to do is you want to distribute your machine across those 5 update domains. And essentially not more than 1 machine will be down at a time. And the availability set also has a concept of fault domains. Now each availability set has 3 fault domains. So essentially all the machines that you put into that availability set, they get distributed across those 3 fault domains. So essentially what the fault domain means is they don't share a common power source and a common switch. And again, the idea is that not more than 1 fault domain will be down at a time. It doesn't always work, but I think it's a close enough approximation. So if you're deploying a replica set in Azure, you should definitely use the concept of availability sets, and you can control exactly which machine goes into which fault domain. Now with all these public clouds, you also have another very interesting option where you can essentially distribute your replicas across multiple regions, right? So that kind of brings us into our next topic, right? So the first thing you want to do is, you want to ask yourself, you want to ask your team, is there a business need for us to be across different regions? And essentially the reason is, to go from multi-AZ to multi-region, the bar gets fairly high. And I'll go into the details of why that is. So the first thing is you got to figure out, is this something you need? Let's say, for example, US East in Amazon goes down, right? And I've talked to several customers, and they're like, that's okay. If US East is down, half the internet is down anyways, so we'll be okay with that. But again, it depends on your business case, but that's a question you need to ask yourself. And the reason is, as you distribute your replicas across different data centers, you run into several problems. The first problem you will have is it comes with security. So there is really no sort of shared code between the 2 regions. So for example, if you deploy a replica in one region and another replica in another region, AWS security groups or Azure network security groups will not work across regions because they're all scoped to a single region. So essentially, if you want to lock down access, you will be responsible for it, and you'll have to work with IP whitelists. You'll have to make sure that you assign static IPs to all the servers, and you have to make sure that you keep a whitelist and assign it and maintain the firewall. And pretty much every single experiment I've seen with IP whitelist so far, it has failed spectacularly. Right? So I don't really believe in working with IP whitelists. It's just a really sort of fragile model. And the second problem you'll see is with latency. A lot of sometimes you have scenarios where the primary is on the East Coast, the secondary will be on the West Coast. So what will happen is, every time there's a write to the primary, it's getting replicated to the secondary. So, across the internet. So essentially, you'll see a lot of latency spikes. So if you are deploying a cluster of this configuration, replica lag is something that you need to be, really careful about. Any questions? I see value in IP whitelisting. I'm very skeptical if it can be done well enough or consistently over a long period of time. Because, here's the first thing. First thing you got to do if you're doing IP whitelisting is you got to work with static IPs. Anything else is just going to be a complete disaster. So you have to make sure all your servers have static IPs, and then you have to keep track of all the static IPs allocated in all the different regions, and you have to make sure all the firewalls are consistent, right? So a lot of times what we find is, people change the they change the IP in one of the nodes, and then you have to go change the IP in all the other firewalls, right? They change it in some places, they won't. Sometimes they'll add local exceptions here, but they won't be in the other firewalls. So when there is a failover, things don't work. So there's definitely value in it. Whether an operations teams can consistently do it over a period of time is debatable in my opinion. Yeah, I think if you're going to do this, you should not even try to do it with variable IPs. It's just a disaster. Because what will happen is, let's say you're in AWS and you don't have elastic IPs. So what will happen is if your server stops and comes back up, in a VPC you'll retain the same public IP, but if you're on a classic cloud, you'll get a new IP. So essentially that node is down until you go in and reconfigure all the firewalls, which is kind of tricky.
Do you deploy other vendors for security
So security comes in multiple layers. So one is the IP whitelist, and the other one I didn't talk about is encryption. So if you're going to distribute your replicas across different regions, then you need encryption at rest. You need to be enabling SSL on all your nodes, because you're now outside the domain of Amazon's data center, so it's going over the internet. So unless you are really comfortable with your data going in plain text across the internet, you need to be encrypting your data. And then similar problems come with backup as well. Essentially, let's say you have a distributed replica set. Do you back it up in every data center, or do you just back it up in one data center? Now, if you just back it up in one data center, what if that data center goes down? So it's not really a strategy, right? So you need to move your backups across all data centers. And the next thing I see is people have high demands of their database, but their application is just sitting in one data center. So that kind of defeats the purpose. So why do you want a highly available database when your application is not highly available, right? So it kind of goes all the way up the stack. Now your application needs to be in different regions, your backups need to be in different regions, and then the database as well. So it can be done. It's very tedious. It requires a very highly functional operations team to pull this off, in my opinion. So let's talk a little bit about Mongo backups. So essentially, there are multiple ways to back up your MongoDB servers. And before you jump into any of these different techniques, the first thing you want to ask yourself, you want to ask yourself a few questions, right? What sort of backup is it? Is it a point-in-time backup? Is it a continuous backup? How long does the backup take? Where are the backups stored? Are the backups encrypted? And the most important question which people don't ask is, how long does it take to recover the backup? Because that really impacts your choice of backup techniques. The first one is essentially the simplest. Mongo has tools called MongoDump and MongoRestore. It's fairly similar to MySQL dump. It's essentially select star from star, and it writes it to a file, right? And then you can move the file over wherever you want, and then essentially you can do MongoRestore and you can replay the file back. Now it's a very simple model. It works very well when you have a small amount of data, but as your data gets larger and larger, essentially that it's unwieldy. And the reason is, MongoDump, let's say you have a 300 gig or a 500 gig database. If you want to do a MongoDump of that database, you are essentially looking at a 3 to 5 hour window to take a MongoDump of that database. And the interesting thing is, it's not point in time as well. So, while your MongoDump is happening, your database is changing on you. So it's not very useful. MongoDump does have an option to do a point in time, but the point in time is towards the end of the backup, not the beginning of the backup, which is what you want. So it's not very useful in my opinion. The next sort of backup which a lot of people use are volume snapshots. And there are a couple of ways you can do this. You can do this inside the OS using LVM snapshots. Like for example, you could mount your Mongo on an LVM volume and take an LVM snapshot. Now with this model, what you have to be careful about is your journal files and your data files. So you want to make sure that both the journal files and the data files, they are sitting on the same disk when you take the snapshot. Or what you have to do is you have to quiesce Mongo. Mongo has this command called fsync lock and fsync unlock. So when you do an fsync lock, essentially Mongo flushes all the changes to disk and gives you a guarantee that it won't write any more till you do an unlock. So if you are using any of these techniques, the snapshots, you need to be using the fsync lock and fsync unlock commands. And those commands are dangerous commands. So if you ever do an fsync lock and you don't do an fsync unlock, your server is essentially locked for writes. So it won't take any more writes. So typically if you do an fsync lock, our recommendation is do it on the secondary and essentially make sure that you're guaranteed to run the fsync unlock. And there are some problems with the LVM snapshots as well. And essentially there are some advantages. The LVM snapshots are diff backups. Essentially, it's a diff of the previous snapshot. So, if not a lot of data is changing, your backups are going to be very small, which is kind of what you want. The problem with LVM snapshots is they're all stored on the same box. So if you want some sort of availability for your backups, then you essentially have to extract the LVM snapshot, copy it over to a different box or a different data center, and then you need to bring it back when you need to restore. And there are some tools to help you do it, but there's a non-trivial amount of DevOps work to stitch it all together and make it work. And the other different type of snapshot, and these are the ones we typically use. They are the cloud provider, volume snapshots. They are basically, EBS snapshots provided by AWS and blob snapshots provided by Microsoft Azure. So they work very similar. You still have to lock Mongo using fsync lock, and then you trigger the snapshot. You don't have to wait for the snapshot to complete, but you just need to trigger the snapshot while Mongo is locked. And then the underlying volume will basically guarantee you that you get a snapshot of the data at the point you triggered it. And it has several advantages. EBS snapshots are essentially diff snapshots. So if you snapshot every hour, it doesn't copy the entire data every hour. It essentially takes a diff from your previous snapshot. So if not a lot of changing, then you greatly reduce your storage size. And the other advantage with EBS snapshots is they stay in the same data center. So if you have some security restrictions, they stay in the same. They're not copied over somewhere else. They stay in the same data center. And you also have some of the security benefits. I'll talk about it as well. If you decide to do encryption at rest, there are some very easy ways to do encryption at rest with EBS snapshots. And by far the most important advantage of EBS snapshots is the ability to restore quickly without network copy. Now, let's say you're running a 2 terabyte cluster in AWS, and something horribly went wrong, and you need to restore the data. Now, if you had used MongoDump and MongoRestore, for you to be able to restore about 2 terabytes of data, you're probably looking at a day and a half or so to get the data up and running, and then data has to sync over and all those things. That's a crucial metric. But with EBS snapshots, what happens is, because no data is physically being copied over, they're all sitting on the EBS volumes, you essentially just create a volume of the snapshot, remove the old volume and attach the new volume and start up your servers. So essentially, the time taken for restore is the same, irrespective of your data size. Now, if there is any crash checks that happen in Mongo as part of the recovery, that's a given, that'll happen. But apart from that, you're not really spending time copying data. Yeah. So EBS snapshots are unaware of that. And that's why you need to use the MongoDB fsync lock and fsync unlock commands. So essentially, just before you're ready for backup, issue an fsync lock. Depending on how big the server is and how much load is there, it can take about a few seconds. What that does is it flushes everything to disk, make sure everything is consistent. It guarantees that no more writes will happen to the disk. Then you trigger the snapshot, and then you unlock it. You don't have to wait for the snapshot to complete. You just trigger the snapshot and unlock it. Because the snapshot might take like 30 minutes to complete, that's okay. But when you trigger it, you need to be in an fsync lock, trigger, and fsync unlock. And we typically do this on the secondaries, because if you do it on your primary, what will happen is your primary won't take any more writes. Does that make sense? Okay. Yeah, so the question was basically, when you do an fsync lock and you're doing a snapshot, what happens to the writes that are coming to the primary in that duration? So essentially, when you do an fsync lock, let's say you do it on a secondary, the secondary says, I'm not taking any more writes, and it doesn't even sync to the primary. And then you trigger the backup, and then you move forward. So typically, this process should take about 3 to 5 seconds. Okay? Now, all the writes that are happening to the primary in that 3 to 5 seconds, they are not synced to the secondary. They will sync to the other secondaries. They will not sync to that secondary, and secondaries that are syncing from, if there's a chain replication setup, then it won't flow downstream. But all the other secondaries that are syncing directly from the primary, they will get the data. And really the important thing about EBS snapshot backup is the fact that you can restore without copying data. Because once your service starts to grow and if you have to restore it manually by copying data over, it's really a deal breaker. And the last option is the MongoDB guys themselves. They have a service called Atlas right now. And essentially it's a backup service. And it works a little differently from EBS or MongoDB, Mongo Store. What they do is periodically, every few minutes, they query the MongoDB op log. The MongoDB op log is similar to the MySQL bin log. So they query the bin log and they upload it to their data center. So essentially, whenever you want to recover, you can just download the data and you can recover. Now, there are advantages and disadvantages of this approach. Now, the advantage is that it's continuous backup. There's no point in time backup. So essentially, you can recover at any point in time. If you're doing a snapshot-based backup, you can only recover to the time at which the snapshot happened. For example, if you set your snapshots to every 3 hours, then essentially you can only recover at those points when you took the snapshots. But if you have the continuous backup running, you can, let's say that you have continuous backup running every 5 minutes. So essentially, you can recover to any 5-minute interval. And the downside of this model is, of course, there is extra cost to it. And the data is also being copied to their own data center. So there is a network copy and download, which for larger clusters is basically, for us is a deal breaker. Because for you to be able to download a terabyte of data from MongoDB data centers, ain't gonna happen. Any questions on the backup? So we talked mostly about, go ahead. The secondary doesn't get the, okay, let me repeat the question. So the question is essentially, when you do an fsync lock, the secondary is not getting the writes that went to the primary. And does it lose those writes forever, or does it ever get those writes back? So the answer is, the secondary doesn't get the writes till you do an fsync unlock. Once you do an fsync unlock, it will start to pull again and will catch up on the lock. So typically, like I said, the typical duration of a lock should be not more than 4 to 5 seconds. Go ahead.
So you've got the two columns there, Amazon and Azure. So you talked about that snapshots for Amazon, but are you actually recommending one of those down in the storage for Azure?
Great question. So the question is basically, what is the recommended model for backing up in Azure? And Azure is a little tricky. It's been changing a lot. Over the what Azure was 2 years ago and what Azure now is now, it's completely different, right? But some things have not changed. The whole Azure compute model, disks are still based on storage accounts and storage blobs. So what we recommend and what we do in Azure is something fairly interesting. Essentially, the Azure Compute API doesn't have any concept of disk snapshots. Like for example, if you go to EC2, there is a disk snapshot concept. EBS snapshots are a first-class citizen in the compute console. But if you go to Azure, Azure doesn't have any concept of disk snapshots, at least in the compute API. So what we do is, we don't use the compute API, but from the compute API, we go in and we reference the underlying blob of that disk, and then we use the storage API to do all our work. So essentially, you can still do snapshots in Azure, but you can't do them at the compute API level. So essentially, you go to the compute API, you figure out which storage blob the disk maps to, and then you open up the storage API, and the storage API has a concept of a storage blob snapshot. So then you can do a storage blob snapshot. And again, that's also like a trivial operation. So you do an fsync lock, you do a blob snapshot, and then you do an fsync unlock. And the downside though in this model is that there is no concept of a diff snapshot or anything like that. So essentially they're all snapshots. It's just a marker on the blob. Now if you want to keep a copy of the blob, then you essentially have to copy over the whole blob. So It's interesting, but I think you can get a long way forward with just the storage blob snapshots, and that's what we use. Go ahead. We are just starting to, and it's getting better and better. And I don't have the depth of knowledge of DocumentDB that we have in Mongo because it's just very early days. Did you have a particular question in mind? Yeah, it's definitely a competitor to Mongo on Azure. I think, okay, let me repeat the question. So, have you considered DocumentDB on Azure and what the pros are and cons are? And I would say that's a session by itself. But, currently as it stands, DocumentDB is getting there, but it's not as mature. And if you look at the core functionality, like, the query models and the indexes, they're just starting to come online, right? So it's a question of what is it you're looking for? Do you not want the operations cost of running your own database, right? If that's the main high order bit, then I think DocumentDB will be very good. So will DynamoDB from AWS. But if your higher order bit is you need a lot of functionality, you need primary indexes, you need secondary indexes, you need range queries, you need group by, you need aggregations, you need to run MapReduce. If you have all those sort of requirements, then I would say, Mongo is still a better option. For how long? Hard to say, because they're moving really fast. And the other question to ask is, what sort of time do you want? Because once you go in with DocumentDB, you're done. You're never going to move off to another cloud at all. So if you're comfortable with that, and if you say, hey, we're going to be an Azure shop, this is where we're going to stay, then, and if your model is very simple, but you need scalability, you need complete lack of operations, then I think it's a very interesting model.
Supports, I forget what the syntax, but MongoDB.
So yeah, so I'm a little skeptical of those sort of things. They work for all the mainstream cases, but the moment you go to the edge case, they'll usually all fall horribly apart. But it can be as long as it's a temporary thing, I think it's okay. But I think if you want to switch to DocumentDB, then you should make the make the real switch and update your whatever data layer to work with that. But it's definitely an interesting option. So is DynamoDB as well. It's in the same sort of bucket. And a lot of customers do use that. Any other questions on backups? So one of the things I forgot to mention is that, if you're on Amazon AWS, it's very typical to store your snapshots on S3 or any sort of object storage. Even on Azure, if you want, you can upload your backups to a particular container and store it. Let's talk a little bit about performance now. And we'll talk a little bit at the high level. So essentially, if you separate performance into compute, RAM, and disk, and if you look at Amazon Web Services, you have a whole alphabet soup of instance types available from generation 1, generation 2, generation 3. It's enough to give you a headache. But at the high level, if you're running Mongo on Amazon, what I would recommend is, choose the memory intensive instance types. Like, if you're looking for R3, essentially, Mongo is typically bound by RAM, and it's very rarely CPU bound. So, of course, your use case might vary, but it's very rare that we see Mongo being CPU bound. So if you're going to choose an instance type, choose one of the memory optimized ones. And there are a few other choices that you can make. When you choose the instance type, make sure it supports EBS optimization. EBS optimization is essentially a feature in Azure, in AWS, where you can block a certain portion of your network just for your data disks. So make sure the instance type you choose enables EBS optimization. And there are a few other options. Like for example, you need to deploy in a VPC, and you need to make sure your instance type supports enhanced networking, which is like a single root IO virtualization, which makes your networking much faster. So when you choose your instance type, those are things you want to keep track of. Now, disks in Amazon are a lot more interesting. So essentially, you have three high-level options when you're doing disks in Amazon. One is the local disks, typically an SSD. they are attached. They come attached to your instance when you bring it up, and they don't cost you any extra. And they're of course very high performance disks as well. But they come with a very important caveat. They are ephemeral. So if you ever stop your instances, those disks go away. So you should be very careful putting your data in a local SSD store. So even if you have 3 copies of your data and all 3 of them are on the local SSD, if due to some reason or some sort of bug, all of the 3 instances get shut down, essentially you have lost all your data. So that's an important caveat to deal with when dealing with local SSD. Now when you're dealing with EBS disks, you essentially have 2 options. There's EBS standard and EBS provisioned IOPS. If you had asked me a year ago, I would have said, don't even bother with EBS standard, just always go with EBS provisioned IOPS. Now with EBS provisioned IOPS, you can essentially buy IOPS for your volumes. You can say, hey, I want this volume to support 10,000 IOPS or 20,000 IOPS. And you can essentially buy that. You can pay money for it. It's not cheap, but it gives you guaranteed IO. So that's what typically I would have recommended, if you had asked me last year. I said, don't bother with EBS standard. But now recently, Amazon has made a lot of changes with EBS standard. Now what happens with EBS standard is you get a base of 3 IOPS for every GB you buy. So for example, let's say you buy a 100 GB disk from Amazon. So essentially what it does is it guarantees you 300 IOPS per second with a 100 GB disk. And it's very interesting. So let's say you don't use the IOPS. What happens is it's like your cell phone minutes, they keep rolling over. So you can keep accumulating your IOPS up to about, I would say about 5.4 million IOPS, you can keep accumulating it. And they will let you burst for up to 3,000 IOPS per second till you use up your burst balance. So if you have accumulated 5.4 million IOPS and you get a burst workload, you can go up to 3,000 IOPS per second. And I think it lasts you about, I would say about 38 to 40 minutes. So it's very interesting. Go ahead. Got it. So the question is, does all the IOPS management and bursting, does it happen automatically? And the answer is yes. If you're using EBS standard, it all happens automatically. If you're using provisioned IOPS, then you need to decide upfront how many IOPS you want for your volumes, and that's all you get. There's no burst mode in provisioned IOPS. Okay. Now, if you're using EBS standard, then your IOPS keep accumulating if you don't use it, and they'll let you use it in burst mode for up to 40 minutes. And there is also a counter, I think it's called the burst balance. So you can go look on your disk, EBS disk, it has a burst balance counter. So if your work, essentially which disk you choose depends on your workload. Let's say you have a workload that's fairly stable and it kind of fits inside the multiply by 3 metric, and every now and then you want a little bit of burst capacity, then I think EBS standard will work very well for you. And it's a lot cheaper than provision. A provision IOPS can get very expensive really quickly. Go ahead.
Good question. I have some familiarity with a lot of the vendors that recommend using ephemeral as opposed to using very penalty using ephemeral versus
Yeah. Got it. So the question is, is there any penalty to using ephemeral SSD disks as opposed to EBS disks? So there really is no penalty per se. The only thing is you need to be aware of the life cycle of those disks. And in a lot of cases, the ephemeral disk will easily outperform the EBS disks. And especially recently, right? If you start the ephemeral disks now, if you look at the i3 instances, they're all NVMe SSDs, so they're really quick, they're really fast and really good size as well. The only problem is if you put all your data on it, you have the risk of losing all your data. Yeah, so it's very painful. So what we do is we have something called a high performance queue, and what that gives us is it gives you a 3-node replica set, and we put 2 of the nodes on ephemeral SSDs, and the 3rd node we keep it on EBS. So essentially what happens is you get the performance benefits of a local SSD from 2 nodes, but in case there's a data center wide outage, the 3rd node preserves your data. Yeah, so if you are using that, I would recommend doing that with your system. No problem. And the other problem with SSD store is there's only fixed sizes, and it's tied to your instance type. So let's say, for example, you run out of the amount of space allocated on your size. That's it. There's no more expanding it. So essentially, you have to go to the next size, which may or may not be what you want. Any other questions on AWS performance? Now let's talk a little bit about Azure. Well, if you thought the instance types in Azure in AWS will give you a headache, wait till you see the instance types in Azure. It's enough to send you to tears, right? There is a standard, there's basic, there's D1, there's DS1, there's DV2, there's DSV2, and there's D11 versus D2. It's really crazy. So you essentially make the time to look through all the instance types, because you can easily pick one that doesn't work for you. So what we recommend is go with the DV2 series. It's essentially a memory optimized sort of workload, and what you're paying for is essentially RAM, and you have low performance CPUs. And in terms of disks, Azure has the same concept. There's a standard disk, there's a premium disk, and there's a local SSD. You can still use the local SSD, same caveats apply as EBS. So essentially, if you stop it, you lose the data. And standard disks, again, fixed IOPS. You can get a maximum of 500 IOPS. And other option is premium storage. So if you're running a high performance data disk in Azure, you should be running premium storage. And premium storage is the Azure equivalent of provisioned IOPS. The only problem is it's not flexible. It only comes in 3 sizes. So you have 128, 512, and 1024. So the 128 GB disk has 500 IOPS. The 512 GB disk has 2300 IOPS, and the 1 terabyte disk has 5000 IOPS. So that's all you get. So you just have to play around with it to figure out what you want. And you'll have to start rating if you want to do something else. Go ahead. So yeah. So the question is, can you grab a number of these premium disks and stripe them or RAID them? And the answer is yes. And there is one other limitation you need to be aware of. There is a instance level network throughput limit, and there is an instance level disk count limit. So for example, some instance will say, your disk throughput is maximum 80 Mbps. So then attaching more disks will not help you there. And other thing to keep in mind is all the sizes have a limit on the number of disks you attach to. I think the largest size will let you attach up to 16 disks. So in some cases, we do like a 16 disk RAID to just get better performance.
You talked about it, and I missed it, but did you have some high level thoughts around standard versus basic, like why you say standard?
Yeah, I think I just skipped over that because the basic stuff is just like for dev and test. Like it doesn't do, I think, load balancing, and there are a few other things. At this point, we never bother with the basic instances at all. We just go with standard. We're running a little short on time, so I'm just going to run through some of these slides. So when it comes to network, essentially, both Azure as well as AWS, they offer a concept of a software-defined network now. So like about 3-4 years ago, if you had deployed on AWS, you would have been on a shared LAN, you would have gotten a IP, and everybody else would be on the same LAN. I think those days are long gone. Now all the hosting providers provide a shared, like a software LAN. So everybody goes into their own space. You can create your own subnets. You can create your own routing rules. And essentially, this is the way going forward. So all of you, if you're deploying on AWS and Azure, you should be creating a VPC, or in Azure case, you should be creating a VNet with subnets. And typically, you should be putting your databases in a private subnet, which is not routable from the internet. We'll talk at a high level about security as well. There's a lot of stuff, the security itself can be a topic by itself. But we'll talk about some simple stuff like, if you're deploying your database on a public cloud, the first question to ask is, who should have access to this DB, right? And then you should be using firewalls to lock down access to this DB. And the ideal recommendation is, don't even expose your database to the internet. and it gives you defense in depth. And like, you guys almost know, like, there were 100,000 people who weren't doing that. So essentially, don't expose your DB to the internet. Go in and start using AWS security groups, and on Azure, they're called network security groups. Lock down access to who has access to the DB. And if you're sending data across regions, I would highly recommend use SSL to encrypt in transit. And if you have compliance requirements, you can also do encryption at rest. I think, for example, if you're on AWS supports the concept of encrypted volumes. Azure also has a concept of encrypted blob storage, so you can do it at the storage account level. So go ahead and leverage that. And if you're looking to scale, once you've deployed, running, everything taken care of, and your workload is ramping up. So if you're looking to scale on public cloud, you essentially have two options. You can scale up or you can scale out. Now, if you're looking to scale up, it's fairly simple. You just go to a new instance type. It'll give you more RAM, more CPU. Just stop the instance, boot it up with the new CPU, and it's done. Disk is a little bit more interesting. Amazon just added the ability to scale disk dynamically. So previously, if you had to do it, you had to take a snapshot of the disk, create a new disk, detach the old disk, and attach the new disk. But as of 3 months ago, you can just, you don't need to do this anymore. Elastic volumes are finally elastic. So you can just grow them in place. Okay? Azure is really tricky. Theoretically, you can resize the underlying blob, but we haven't successfully been able to do that. So the problem happens, and what happens is, we are also running RAIDs on top, so it becomes a really complicated problem when you're in RAIDed disks and you're resizing disks. It requires a high level of expertise. So in Azure, even though we don't like it, we just end up rebuilding new disks. And scale out is one of the nice things about Mongo. If you're running a shard and you want to scale, all you have to do is go in and add a new shard, and then everything is magical after that. Mongo goes in and it'll rebalance the data, and it'll start moving data to the new shard. And essentially, there's nothing you have to do but add the new shard, and everything else is taken care of. The only drawback is, it takes a while. If you're running large shards, to sync up a new shard and distribute everything, you're looking at an order of days for everything to balance. And while the balance is happening, stuff is still up and running, so it's happening in the background, so there's no downtime, but it's something to prepare for. So if you've already hit the scale point, it's too late to scale. So you need to shard and scale before you hit your scale points. And once your clusters are running in production, essentially there are some common operations that you need to do. Like, you need to be patching your OS every whatever cycle you want, every month or every week. And Mongo also doesn't auto-compact its data files. So if you have a lot of writes and deletes happening, your underlying files get fragmented. So you have to run compact to essentially defragment those files. And of course, make sure you monitor all your servers. You should be monitoring all the OS metrics, like CPU usage, RAM usage, disk usage. And you should also be looking at all your interesting Mongo metrics. Depending on the storage engine, you might want to look at the lock percentage, the read-write tickets, the connection count, and pay close attention to disk queues and replication lag and all these things. And then the last one is, keep track of all the queries that are happening in your system. And we have built a query analysis tool where you can go and pick a time range, and then it'll analyze all the queries and tell you, which one's the most frequent, which ones are scanning the most rows, which ones are returning the most rows, which ones are causing the most locks. So there are plenty of tools out there. So you should go start to use one, and that way when your developers add a new query which they didn't index, you'll find it fairly easy. I'm not sure. Maybe we can chat offline. I can talk about it. The question was, is there any open source tool to do query analysis? I'll have to think of. I think there is. I forget the name of that tool. There is a tool to do query analysis. Essentially, it takes the log files and gives you a graph. That's it. Any other questions? Well, if you guys have other questions, I'll be around, so you can ask me. Thanks, guys.